Graph is one of the most widely used data structures in programming and is often asked in coding interviews as well. Hi, my name is Prateek, and in this tutorial we'll be understanding the basics of graphs, its applications in various domains, and its representations such as adjacency list, adjacency matrix. In the next set of videos, we will be diving deep into graph algorithms and learn to code them. But before we get started, make sure you check out free masterclasses on Scalar's event page to learn from industry leading experts. Also, subscribe to our channel if you haven't done already. Let's begin with the tutorial. So let us talk about graph. So graph is a network like data structure consisting of nodes and edges. So it is a data structure, that means it is able to hold data, and the data is in the form of a network. Okay, and consisting of nodes and edges. So if I look at this figure, all these circles, they represent a node, and all these lines, they are representing a connection between these two nodes. For example, this edge is connecting node 4 and 25. So can we think of any real life example where the data might have connections in between certain objects? Of course, yes. If we talk about cities, then cities are connected with each other through connections which we call as roads. If we talk about a social media graph, for example, this is person A and he is connected with a person B, and A is also connected with a C. So we say B and C, they are friends of A, or A and B are connected, A and C are connected. If I talk about this person D, is it connected to A? We say no. The person A is not connected with D, or D is not connected with A, because there is no direct edge in between them. So if I add a edge, they also become direct connections. So there can be many applications in real life where graphs can play an important role. So let us try to understand the applications first, then we will dive deeper into the implementation and coding. So graphs, as I said, they are used in many real life applications and they represent a network of nodes. Such a network of nodes can be a network of cities, a network of places, landmarks, anything. It can also be an electrical circuit. When you use your mobile phones, it has something called as a circuit. Okay, it has a motherboard on which you have certain elements, certain small embedded systems on it, and there is a wire connecting these any elements. So it is possible that we want to find out the most optimal route for the wire so that we can reduce the cost. Okay, because it is a copper wiring, it can be expensive. It can be a graph algorithm can be used here to minimize the total length of the wire that can be used to connect all the components in this circuit. And of course, social media networks, we have just discussed that Facebook, Twitter, LinkedIn, all these networks, they can represent graphs. So let us go into the applications in little more detail. The first example is an example of shortest paths. We often use apps like Google Maps, Uber, Ola, and many other apps to compute to in our daily life. Okay, so these apps, they try to figure out what is the shortest path between the set of nodes that are there, and should I go from this route or should I go from this route. If you want to do such a calculation, okay, if you want to go from source to a destination, then what path would be best can be easily devised using a shortest path algorithm known as Dijkstra's shortest path algorithm. We will discuss that algorithm in this series. Then of course, if you want to book flights, okay, you want to say, okay, I have to go to this region. Maybe there is a flight which costs 80 and there is a flight which costs 20. Should I take this flight or should I take these three flights? So maybe they are cheaper, but they are taking more time. So there might be trade-offs. Again, you have to look at what you want. What is your requirement? Do you want to optimize for time, or do you want to optimize for the total cost of travel? The social media networks I have discussed. So I will give you one more example. In some networks, when you connect with a person, for example, Facebook. So if A and B are friends, then this connection is bidirectional. That means A is connected with B, B is connected with A. But in some other networks, this connection is having a direction. For example, on Twitter, if A follows B, it does not mean B is also following A. So these edges, they can be bidirectional or they can be one directional. So we call such a graph as a directed graph or directed edges. Okay, so this graph has directed edges because A is following C and B, but B is not following this. So in such a case, this is called as a directed edge. And in example of Facebook, it is called as a undirected edge because there is no fixed direction. If A and B are friends, then B is a friend of A and A is also a friend of B, right? Now these kind of representations, the graph like representation is important to build algorithms. If you want to find mutual friends, if you want to generate news feed, so for A, it will see the post from B and C. If B is following someone, then this person's post will not be visible to A. So all these algorithms require graph like representation of the objects involved. Then there is also something called as shortest round trip. If you think of if you think of something called as a school van, okay, what is the purpose of school van? It will start from school and it will drop all the children on the way and it will come back to its location. So in this case, what is happening? We are doing a cyclic tour. We are coming to the source by covering all the points in the city where we need to drop the children. Now it is possible that multiple routes can be devised, but we want to devise a route which costs minimum. So such route design can be used in for Amazon delivery vans, for school vans, and this is a very famous problem in graphs called as traveling salesman problem. We will also discuss this problem in the coming series. Let us talk about one more application. So when you are installing software, you might have seen that the software is installing list of dependencies in a certain order. For example, you have to install a software X. For X, you need something called as, let's say, C. C is dependent upon something called as B. B is dependent upon A. And there is something called as D. X is dependent upon D and D is also dependent upon A and B, right? Now, in such a scenario, if I have to install the dependencies, what is the first thing I will install? Of course, I will install A. If I install A, then B and D, they do not have any dependency. So either I can go with B or I can go with D. So I can install B and D. If I have installed B and D, then X has only one dependency, that is C. So I can install C and then I can install X. So if I install the dependencies in this order, right, my software will be installed correctly. So this kind of a graph, it is called as dependency graph and it is an example of a directed acyclic graph. That means there is no cycle, it is directed. And from this graph, we need to figure out what is the correct order of installation of software, right? So it is often used while installing software on systems, on servers, when you're installing libraries and modules. They follow this particular order, and this dependency graph can be easily created using a graph algorithm called as topological sorting. We will learn about this algorithm in the coming series of videos. Okay, so that is another application of graph. So let us talk about one more application, that is routing algorithms. So Bellman-Ford is a very popular graph algorithm that is also used in finding shortest paths. Now this algorithm is also used in routing algorithms. So the world has lot of routers, right? And these routers are continuously exchanging data packets. So which data packet should go there and what is the shortest time in which it can reach to the desired location? So all this routing is done using a distributed version of Bellman-Ford algorithm, which is again a very interesting algorithm in itself. So let us talk about one more application. So if some of you have done machine learning, then you know in deep learning, the deep learning models, they do gradient computation, which is an important step in training of the machine learning models. Okay, so these gradients are used in back propagation to adjust the model parameters, and the way these libraries like TensorFlow, PyTorch, they build a computation graph of these gradients so that the computation can be optimized. So you do not need to worry about how to construct the graph. The libraries like TensorFlow, PyTorch, they automatically do it for you. Again, this is inspired from the idea of graphs itself. And in traditional computer vision, what happened? Image segmentation algorithms were used, which were based upon the concept of network flow, which is again a graph based algorithm. So if you do not know what is image segmentation, so image segmentation is basically extracting out objects from an image. It's like drawing a boundary on an object that is like one entity. In case of this example, the car is one object, the building is another object, this footpath is another object, the road is another object. So these kind of algorithms are often used in self-driven cars, but in today's world we have deep learning techniques for image segmentation, but the traditional way of doing this segmentation was based upon a graph algorithm called network flow. Again, let's do one more application in web crawler. So basically, when you want to build a web crawler, for example, you want to crawl amazon.com and you want to scrap the entire website. So when you go to amazon.com, what happens? You load the code is loaded in the browser. So in the code, you will see there are a lot of products, and with each product, there is a hyperlink. So you want to go and scrap all those products. So what do? You build a web scraper that reads these links, adds them into queue. Maybe this is some TV button. Okay, so you go to that page, it opens up, and then again there are many links here. So you can also use these links to crawl further, right? So it's like a tree traversal. So web crawlers use breadth first search to crawl the web. So if you have built a web scraper, you would have know that you often do a BFS like thing, and you traverse the DOM tree, and a tree is also a graph. Okay, a tree does not contain a cycle, but it is also a graph example. So let us do one more application. So nowadays, we also have databases that are inspired from the idea of graphs. One such database is called Neo4j. So these kind of databases are used in recommendation engines, fraud detection, and many AI based applications. Apart from it, there are a lot of other applications of graphs, such as in linguistics, social sciences, biology, neuroscience, atomic and molecular structure, computer processing, flood fill, and more. So what is this flood fill? This is an interesting application I often cover in my course. When you use the paint bucket tool like this and you drop it in an object, it automatically fills the color till it hits the boundary, like you can see here, right? So this again is an example of graph, and this matrix is an example of a 2D implicit. It's a 2D matrix which is representing a implicit graph. So we will discuss about what is an implicit graph and how do we build algorithms on implicit graph. That will be covered as well. So that's about the applications. Next, we will dive into the more technical concepts and understand how a graph can actually be created and stored inside the memory. Next thing I want to talk about in graphs is classification of graphs. Though we have talked briefly about weighted and unweighted graphs, let us try to understand with some more examples. Basically, there are two criteria for classifying graphs. One is weight of edges. There can be graphs in which there is no weight associated with the edge. That means each edge is treated equally. Each has a unit cost. Okay, you can say, okay, it is a unweighted graph. Such a graph is called as unweighted graph. But it can be scenario, for example, if you talk about roads. So each road might have a length, or it might have a time to travel from B to C, right? So some kind of weight or maybe some kind of fuel cost. So we can say that in such a scenario, each edge is having a different weight, and we need to store that weight as well. Okay, so earlier if I'm representing a edge as a comma b in an unweighted graph, now I have to represent edge as a comma b comma 10. That means the time to travel from A to B, or the edge weight from A to B. So this is a case of a weighted graph, right? That means in the implementation also, we will have to store this weight associated with the each edge, and then there is direction of edges. Now there can be scenarios where the edges are not having any specific direction. For example, talk about Facebook friends. If A and B are connected, they are connected. That means A is a friend of B, B is a friend of A. But edges can have a certain direction. For example, a Twitter graph. So if A is following B, does not mean that B is also following A. So in this case, edge will have a certain direction. That means A is following B and A is following C. and B is following C, something like this. This is an example of a directed graph, and wait, so this is an example of undirected graph. Let us look at some more examples. Okay, so we have discussed graphs whose edges or paths can have values associated with them. They will be called as weighted graphs. Edge value can represent either the weight or some kind of cost or length of that path. For example, in roads it might be the distance in kilometers. So directed undirected graph we have already discussed. Graph edges can have specific direction attached to them. They're called as directed graphs. Okay, now in such a scenario you might have two-way edges. For example, from 1 to 2 there is an edge, from 2 to 1 there can be edge as well, and it is possible a different weight is associated with each of it edge. For example, we are going from Delhi to Bangalore via flight. Now this flight might cost you 4k, but this flight might cost you 5k. So this is an example of a directed and a weighted graph. In an undirected graph, there is no direction of the edge. That means you can travel in both directions. You can go from A to B, you can go from B to A, for example, in roads. Okay, so I hope you are able to understand through these examples. So let us try to make a matrix, and let's summarize, right? So I can say graph can have weights, weighted graphs, or unweighted graph. They can have direction or they can be undirected. Okay, so what would be an example of a directed and a weighted graph? For example, from A to B, okay, and there is a cost associated with it. This can be your graph of different flights across cities, because flights will have a cost and they will have a direction. So if there is a flight from A to B, it is possible that there is no flight from B to A, or B to A flight has a different cost. This will be a directed and a weighted graph. Let's look at an example of a directed and unweighted graph. I talked about topological sorting, in which we said that there are certain tasks and there are dependencies. For example, B is dependent upon A, C is also dependent upon A, and C is also dependent upon B. So this is an example of a directed acyclic graph. Okay, so this is an example of a dependency graph. In this graph, there is a direction, but there is no weight. It is an example of directed and unweighted graph. So an example is dependency graph. Okay. Then there is an example of undirected but weighted graph. So I want a graph in which there is no direction, but there is a weight. Maybe the road network, I can say, okay, the roads are generally two-way. So there is a cost, so there is a weight, but there is no direction. So 100, 200, 10, 20. This is an example of a undirected and a weighted graph. Then undirected and unweighted graph. So that means no direction and no weights as well. So it could be simple Facebook graph in which you are representing who is connected with whom. A and D, they are friends. So there is no weight. So maybe Facebook friends graph, okay, or Facebook network. So it is possible that it is unweighted, but depending upon how Facebook implements it, this graph can also become weighted. Facebook might represent a score, a friendship score on each edge, how strong these two people are, how strong their bond is. So it is possible that this graph can be made as weighted also. So I hope classification of graphs is clear through these examples. And next we will dive into the implementation, how to create a graph and store it on your RAM. Now the next question arises, how do we actually create this data structure and how do we work with it? So there are three common representations for graph. One is called as edge list, one is called as adjacency matrix, and one is called as adjacency list. We will go over all of them one by one. Each representation has its own set of advantages and disadvantages. But in general, this representation, which is called adjacency list, this is the most popular and most commonly used in many algorithms. But this does not mean that edge list is useful or adjacency matrix is useless. They are also useful. They have their specific applications in certain type of algorithms. So let us discuss edge list first. And what is a edge list? So in a edge list, we represent graph in terms of list of edges, right? So suppose we have vertices A, B, C, D. So we will make a list of vertices, and if we have edges, we will note down what edges we have. We have AB, so AB is an edge. We have AC, we store that. We have AD, we store that. We have BC, we store that. We have CD, we store that. So right now I'm assuming this is a undirected graph. So when AB is an edge, it also means BA edge is also there. That means if you can go from A to B, you can also go from B to A as well, right? Similarly, if you can go from A to C, you can go from C to A as well, right? So in my code, I will be storing two copies. AD is there, DA is there, BC is there, CB is there, DC is there, right? So I'll be storing it like this. That will be more helpful, because if I am at D and I want to look at what nodes I can visit, so I can clearly look at this. There is an edge from D to A and there is an edge from D to C, right? So I can look at this. Or you can say, okay, I'll iterate through the whole list. Of course, you will have to iterate through the whole list and you have to look at what pairs contain D, right? From that, you can get this information from D where you can go, right? But this kind of representation is pretty, I would say, inefficient if you have to find whether there is an edge between, let's say, B and D. I want to see whether there is an edge from B to D. The answer is it is inefficient, because you have to do a linear search over the whole list. So that means you have to spend order of E time looking for whether such an edge exists or not, right? Similarly, if you have to do an operation like, okay, give me the neighbors, immediate neighbors of B, right? This is now a very common operation in graph algorithms such as BFS, DFS, Dijkstra's. We often need this operation, right? So neighbors of B. So what are the neighbors of B? So again, you cannot tell directly. You have to iterate over the whole edge list to find out what are the neighbors of B. Again, this operation is going to be inefficient. It is going to take order of E time, right? But one thing this edge list is good at, for example, suppose this this graph was a, let's say, a weighted graph, let's say 10, 5, 2, 1, 6, right? And I want to pick edges based upon their weight, right? So now in such a scenario, I will be storing three things in an edge. So I will be storing A, B followed by 2. I will be storing A, C followed by the weight, right? In case of a weighted graph, I need to store three things, right? And so on. Maybe I want to pick edges based upon their weight. So what I can do, if I've stored all edges in the form of list, I can easily do sorting on this list. Okay, I can do sorting on the list in like E log E time, right? E log E time. And I can pick edges maybe based upon their weight, right? So, or according to some criteria, right? So maybe I want to do sorting on the list based upon weight of edges. So this kind of algorithm is actually helpful when we deal with a topic that is called as minimum spanning tree, right? So when we are building a minimum spanning tree algorithm, we actually need to pick edges based upon weight. So in such an algorithm, we will go with the edge list kind of a representation, right? So that means this representation is also useful, but it depends upon the algorithm. What kind of operation do we want? Do we want to get neighbors of a node, or do we want to sort edges? So if we want to sort edges, then edge list is the representation that we will use. So I hope you are able to understand edge list. And now in the next video, and now we will discuss the code of edge list. So I'm going to show you how we can create a graph using edge list. So I am in my IntelliJ IDE and I'm going to create a class called as graph using edge list. This class will be responsible for holding the data of the graph. So effectively what I'm going to do is I'm going to keep things little simple. I'm going to fix number of nodes. Let's say number of nodes is given as input by the user. Let's say user says 4 nodes. I'm not going to take input the names of nodes. I'm going to assume that the nodes are always numbered from 0 to n minus 1. So this is from 0 to 3, right? This is something which is very common in many coding problems, and we often we make this assumption, okay? And you can also verify from the problem statement. If this is not the case, then we will discuss it separately, right? The number of nodes are 4, and let's say the graph looks like this: 0, 1, 2, 3, right? So what is expected in the input? that you will be given how many edges are there. So number of edges will be input, that is also 4, and then you will be given the names of edges. So 0 comma 1 is one edge, 0 comma 3 is another edge, 1 comma 2 is another edge, 2 comma 3 is another edge. So you will be given these numbers input. So what is our expectation? That this graph should be able to hold these pair of edges. So 0 comma 1 I want to hold, 0 comma 3 I want to hold, 1 comma 2 I want to hold, and 2 comma 3 I want to hold, right? Now if you look at this list, can you visualize this graph? Of course yes, right? That means this information is sufficient to store this graph, right? So what I'm going to do in this graph class is I'm going to make a list which is able to hold a following edge, right? Now it is possible that each edge might have a certain weight, let's say some weight w1, w2, w3, w4, right? So in such a scenario I can add w1, w2, w3. It will be list of edge where each edge object is a collection of 3 numbers in this case, right? So what we can do is we can define a class called as edge, right? We can define a class called as edge, right? And in this class I can have 3 things. One is maybe the source, so I call it as u. I have v and I have weight, right? So that means the triplet. So if there is an edge from u to v with a weight w, I'm going to store a triplet u v w, and I'm going to create an edge object out of it, right? Then I can make a list of edges. So I hope you understood the concept. Let us dive into coding. So I need a constructor for the edge class. So the constructor is going to expect u, v, and w, right, for one edge object. So I can say this dot u equals u, this dot v equals v, this dot weight equals weight, right? So later on I want to print the edges, so I might need a method to display an edge, right? So I can just use the toString method, which is going to show me, which is going to print, which is going to return a string representation for this edge. So this will be helpful when we are going to print the edge. So if I want to do s out an edge, I will see that the edge will be printed like this: u equal to something, v equal to something, and weight equal to something. This overrides the default toString method, right? And it is auto generated by the id for me, right? So I have the toString method with me, right? This will be helpful if I'm going to display the graph. That means I'm going to display this edge list in the output. So I don't have to write for each edge. I don't have to do this work because this method will be called when I'm going to print it. So I can simply say s out some edge, right? So something like this we can do. So now coming to this actual class, right? So let's make this class as public. In this class, what information it needs to hold? It needs to hold how many nodes we have, number of vertices. Number of edges is optional because it can be judged by the length of this list, right? So user is going to enter the edges and we are going to store them, right? So that is simple. And so let's have a constructor, right? So the construct, and apart from it we need a list of edges, right? So list of the type edges L. Let's create the constructor graph using edge list. So in this constructor I'm going to get number of vertices which I can initialize. So this will be list of edge. So I can say this dot v equal to v, and I also need to create this list. So L is a new list, so it can be a linked list or an array list, and I can say it is an empty list, right? So when a graph is created, it knows how many vertices it has and it creates an empty linked list. Okay, now I want to add edges in this graph. So maybe I need to create some method add edge u comma v and weight, right? I want to push an edge into this graph. So I can simply say uh, if there is an edge from u to v, so I can say um, L dot add. What I should add? I should add a new edge which goes from u to v and is having a following weight. So I'm doing it for a directed graph, right? I'm doing it for a directed graph. So I think this implementation looks complete to me. Now let us test our implementation by going to main, right? So here what I need to do, I need to create a graph object, right? Which I am doing, right? And then I'm saying that fine. Okay, so here I've passed one more parameter which is going to tell whether the graph is directed graph or undirected graph. So this is an optional thing. If you want to accept that okay, this is a directed graph, then you can add just this edge. But if it is an undirected graph, you also need to do one more uh, line of code where you are adding the edge from U to V, right? So you're saying that okay, A and B are connected. That means A is a friend of B. There is an edge from A to B, but there is also an edge from B to A, right? So you can do this thing in case of a undirected graph. So that can be handled by putting a if condition here. But for now, I'm keeping things simple and I will modify this code a little bit. Earlier, I did it for undirected graph, right? So it's just a signal to the graph whether you want to add this edge like one time or two times, right? And now I want to display the graph. I basically want to display the edge list, right? So I created a graph object using this class new graph. I initialize the number of vertices, which actually we are not using as of now, but this might be helpful in future, right? For some other use case. Now if I want to display this edge list, so I can say okay, void display. Okay, or let me see if I can do a toString thing here, right? So here I'm going to modify this, right? I'm going to, or this is fine actually, this is fine. So it is going to return a list. Let's see what does it return, right? So I'm going to say sout graph, show me the graph, right? So let's go and run this code. Okay, so this graph says that okay, I know two things. I have vertices which are 4 and I have a list of edges which is this list. Okay, so there is an edge from 0 to 1 with weight 10. So 0 to 1 weight 10, 0 to 2 weight 20, 0 to 2 weight 20, 1 to 2 weight 30, right? So you can see this is completely fine and we are able to see uh, the edge list that we have implemented. So that is the idea behind edge list. Now you can use this edge list to do sorting. So right now I have hard coded values here, but what you can do, you can ask the number of edges, put a for loop, take input those edges, and inside the loop you can call this function g.addEdge, and this is going to add all the edges in your graph, right? So in generally, I've discussed how the input is given, number of nodes is given, number of edges is given, followed by list of edges is given, right? So pairs like 0, comma 1, comma 10, followed by next pair 0, comma 2, comma 20, right? This will be input. You can scan it and call g.addEdge to add it in your graph, right? So I hope this representation is clear. Next, we will discuss another implementation. The next representation of a graph, it is called as adjacency matrix. So what is this? It is a 2D matrix which is of the size v cross v, where v is the number of vertices of the graph. The number of elements in the matrix indicate whether pairs of the elements of the matrix, actually not the number of elements. The element of the matrix indicates whether pairs of vertices are adjacent or not. Basically, if there is an edge from 1 comma 2, right? So what we will do, we will have a adjacency matrix. Okay, so in this case there are 5 nodes, so there is a 5 cross 5 matrix, right? And there is an edge from 1 comma 2. So what we are doing, we are saying that matrix of 1 comma 2 will be true. So if it is a unweighted graph, there is no weight, so I can simply set this edge as true. So 1 comma 2 is true, or it is 1, right? And similarly, if it is a undirected graph, there is no direction, so matrix of 2 comma 1 is also true, right? So this value is also true. So this value 1 comma 5, this is 0. So this basically indicates there is no edge from 1 to 5, right? So if there is an edge from x comma y, then in my matrix of x comma y will be set to 1, and matrix of y comma x will also be set to 1. That indicates that x and y, they are connected, right? So this is pretty simple. And the problem with this approach is that as your n grows, right? So if let's say you have 1000 nodes, right? Your matrix will be of the size n square, right? So that means it will have 10 power 6 elements. So if n is let's say 10 power 7, your matrix will be of the size 10 power 14. You won't be able to hold this big matrix in your memory, right? So it is not suitable for large number of nodes. Okay, it is suitable for small number of nodes, but again there are certain advantages and disadvantages for this, right? One is, one disadvantage is that you are going to waste a lot of space. So in most of the graphs, if you have n nodes, you might not have n square edges. That means lot of zeros will be there in the matrix, which is leading to space wastage. Secondly, if you want to find neighbors of 1, what nodes are connected with 1? There is no way, you have to iterate over this whole list, which is going to take order of v time, right? Because there are v vertices here. You have to go to each vertex and check whether one is connected with it or not, right? That is again a problem. We do not want to go to 5 because one is not connected with 5, but we are still iterating, right? So this is a major disadvantage. That means you cannot get neighbors of a node. In order to get neighbors of node, you have to spend order of v time, which is not very efficient operation, right? But there is one advantage as well. So what is the advantage? If I have to check if there is an edge between 1 comma 3, right? So that check can be order 1. Why? Because you just need to go to 1 comma 3, this index, and check yes, this value is 1. So you can check yes, this value is 1. So that means I can figure out whether an edge is present between two nodes or not in just order 1 time, right? Now you might ask, what if the graph was a weighted graph? 1 comma 2 was having, let's say, w weight. So in such a scenario, instead of storing 0 or 1 here, you will store 0 followed by weight, right? 0 and weight. So 1 comma 2 has having w weight, so 2 comma 1 is also having w weight, right? So you can store integer values. 2 comma 5 has 8 weight, so 2 comma 5 you can put this value as 8, and 5 comma 2 as also 8, right? So depending upon the use case, this matrix can be an integer matrix or it can be a boolean matrix, right? So I hope you understand the concept of adjacency matrix. Now let us look at the implementation of adjacency matrix. Let us implement graph using adjacency matrix. So again, I will have to keep number of vertices and I will have to keep a boolean matrix. So I can say a boolean some matrix, let's say called adjacency matrix, and we will initialize this matrix in the constructor, right? So I have graph using adjacency matrix. I'm getting the number of vertices. This dot v equals v, and adjacency matrix equals new boolean of the size v cross v, right? So I hope this matrix, this initialization is clear. By default, I think all the values would be false, and now we can write the add edge function, right? So I'm not going to take the weighted graph because I've taken a boolean matrix. So I will take only two parameters, the edge from u to v, and also I'm assuming the graph is a undirected graph, right? But if you have a directed graph, then it is even easier, right? So if there is an edge from u to v, what I need to do in the matrix for the uth row and the vth column, I need to mark this as true. So I can say adjacency matrix of u comma v will be marked as true, rest everything is false, right? And adjacency matrix of v comma u, this is also true, right? So the other way around we also have to do, right? So that's it. Now what we need to do, we need to test our code, right? This adds an edge to our graph, and now we can have a display method, right? That is going to display the matrix. So I can add a toString method here, which is going to display the vertices and the adjacency matrix. Let's go to main here, and now I have to create a graph using adjacency matrix. So I've added a few edges, and now let us go and run this code, and let's see what output do we get. Now we are getting, okay, in this graph object we have 4 vertices, And now adjacency matrix is being displayed like this. So this is actually how a 2D array is stored in Java, right? So if I talk about a 2D array, the 2D array is a 1D array of rows, right? And each row is actually is storing the address of an array, right? This is how it is being done, right? This is how it is actually done. 2D array is an array of rows, and each row is, let's say this row is 30C, this is 97D, right? So what we are printing is, we are printing the address of each row of the array, right? So this is the address of a 1D array, 0th row, first row, second row, and third row. If I want to handle this in a correct manner, right, so I have to say that we do not want to convert this 2D matrix into string directly. We have to use a method called deep to string that will actually iterate deeply into each row, and then it will convert the contents into the string, right? So I'll do it like this. This will actually give me the string like representation of the full 2D array, right? Let's go and run this code once again and see what do we get. Yeah, this time I'm getting the correct adjacency matrix. So I will draw it for you. So what I did, I give 4 vertices, let's say 0, 1, 2 and 3. Then I said 1 and 2 are connected, fine. 0 and 3 they are connected, okay. 1 and 3 are connected, okay. And 2 and 3 they are connected, okay. So this is how the graph looks like. And then I have a 4 cross 4 matrix, 0 1 2 3, 0 1 2 3. So it is false 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 true. So here I have a true here, false false true true. So here I have true true, false true false true. So true true. Then I have true 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 false, t t t. So if you look at this 0, so 0 is only connected with 3, so we have a true here. Then look at 1, 1 is connected with 2 and 3, so 1 is connected with 2 and 3, correct? Look at 2, 2 is connected with 1 and 3, 2 is connected with 1 and 3, correct? Look at 3, 3 is connected with 0, 1, 2, so 0, 1 and 2, yes. This is a correct representation of the adjacency matrix for this graph. So I hope you understood this concept, pretty easy, nothing fancy in it. And you can easily modify the code for a directed graph by making this as a integer matrix and putting the weight here, right? So that's all. Next we will discuss adjacency list. Now let us talk about one more implementation of graph that is called as adjacency list. So this is the most widely and most common used representation in many graph algorithms. What do we do in this representation? The adjacency list represents a graph as an array of linked lists. The index of the array represents a node. So we will try to understand. Now suppose I have 1 to 2, there is an edge, right? So what I really want to do is that with node 1, I actually want to store all the neighbors of 1. So 1 is connected with 2, 1 is connected with 3, 1 is connected with 4, right? So basically there is a key value mapping. So key is 1, value is the list of nodes with which it is connected. One way to store it is that we create an array. Now suppose there are 5 nodes. So here they have assumed a 1 based indexing, but in our code there will be a 0 based indexing, right? What it is saying that it is a linked list, right? So if you talk about 1, 1 is connected with 2, 3, 4. Similarly, if you talk about 2, 2 is connected with 1, 3 and 5. So I know 2 is connected with 1, 3 and 5. 3 is connected with 4 and 2, right? So and 1 also. So it is connected with 1, 2 and 4. 4 is connected with 1 and 3, and 5 is connected with 2, right? So each of this is like a linked list. We can definitely add more to this linked list. For example, if 5 and 6 are connected, so I can say, okay, in linked list of 5 you can add 6, and in 6, at the 6th position you can add 5. Okay, so why we are using this linked list? Because it is easy to add into this, so we can easily do a add operation, right? But how many linked lists do we need? Do we need one linked list? No, we need an array of linked lists. So this data structure is an array of linked list, right? So right now we are assuming a one based indexing, but it will be zero based indexing. If I talk about array of one is nothing but it is a list. What about array of two? Array of two is nothing but it is a list. And what does array of two denote? Array of two denotes a list containing neighbors of two, right? So if we implement this, right? So what we are going to store? We are going to store this, and we are going to form an array out of it, right? So this is what an array of lists look like. Some of you might ask, what happens if nodes are not numbered 1 to 3? Suppose they are numbered as Delhi, Mumbai, Jaipur. In that case, instead of using an array of lists, you can also create a hash map, right? Where the key is a string and the value is a list of string. That is also possible, right? That is also a way to implement a adjacency list. So in case of zero based numbering, it becomes easy because array indexes are numbers themselves. But if you have something complex like Delhi, Mumbai, Jaipur, Ahmedabad, you can also use a hash map in place of it, right? So I hope you are able to understand this concept. Now let us talk about advantages of this representation. So the first advantage is efficient storage. We are not wasting any space, unlike we did in adjacency matrix, right? So we are only storing the value of edges where the edges actually exist. So it is efficient in terms of storage, right? They are also useful for storing sparse graphs. That means um, which have much lesser edges compared to, like, what will be a dense graph. So if you have five vertices and you have, let's say, v square edges, in that case that means every node is connected with everyone. In that case adjacency matrix can be easily used, right? But if you have five vertices, seven edges, it's kind of a sparse graph, right? Number of edges is much less than v square, right? And the biggest advantage is efficient retrieval of neighbors. As I told you that this is an important operation that we frequently do in algorithms like BFS and DFS. We can easily find neighbors of any node. If I ask you, okay, find neighbors of 3, what you need to do? You need to go to array of 3, which is an order 1 operation, and then you need to iterate on this list. So basically in order of neighbors time, if 3 has 3 neighbors out of 100 nodes, you can get those 3 neighbors in 3 units of time. You don't have to traverse the whole list of nodes, right? So this is a very efficient operation. Because of these two reasons, it is a very widely used. One is efficient storage, second is efficient retrieval of neighbors. This makes adjacency list a popular choice for graph representation and is used in many algorithms such as BFS, DFS, shortest path algorithms, and much more. Now let us discuss implementation of adjacency list. So let us start implementing graph using adjacency list. So we are discussing adjacency list implementation for the graph. So one thing we need is the number of vertices. Next, what do we need? We need an array of linked list. So how do I create it? I can say list of what? List of integers. If I simply write adjacency list, this makes one list object, but I need an array, right? Now I need to initialize this array inside. Okay, this will be integer here, right? Because my collections does not accept primitive data types. I need to initialize this object in the constructor itself. What is the size of this list? That will be known when we are creating the graph object. So I can get the number of vertices, and I can say this dot v equals v, and I can say this dot adjacency list, this is equal to new linked list of integer. And how many objects do I need? I need v number of objects. Okay, so I have created an array in which this adjacency list, right? But right now this object is not created, right? Only an array is created. So what I need to create? I need to create a linked list at each index. So how do I do it? So I can say, okay, I will iterate over this I equal to 0, I less than v, I plus plus, right? So basically, when I say I'm creating this array, that means the array bucket can hold the address of a linked list. But right now that is null, right? So what do I want? I want this bucket to hold the address of a linked list object. So how do I create this linked list object? I have to use new, right? I have to say adjacency list of I. This is equal to new linked list. This actually creates an array in which each element is a linked list object, right? So this is the correct way of constructing a adjacency list. Now what do I need to do? I need to add elements into the linked list, right? So I will have a function called void add edge. So edges from u to v. What do I do now? I can say, okay, if there is an edge from u to v, what should I will do? And maybe I can accept, is it a undirected graph, right? If it is true, I will also add an edge from v to u, right? So I can say adjacency list of u dot add v, something like this. And if it is a undirected graph, I can say adjacency list of v. Oh, it will be boolean, right? Bool is in C++. Adjacency list of v dot add, something like this. Basically what I'm saying, that go and add an edge from 1 comma 2. So 0 1 2 3. So in first link list it will add 2, and in second list it will add 1. Then I say, okay, go and add 1 comma 3. In first list it will add 3, and in third list it will add 1, something like this. Basically if 1 is connected with 2, 1 is connected with 3. So if I read this, I see 1's neighbors are 2 and 3, right? So if I write it little more clearly, so 2 and 3, they have been added into the linked list which is at the first position, right? So this is how the add edge function looks like. Then I can display the graph, so I can write the toString method which is auto generated. And here, similar to the previous case, normal toString will not work. I want to iterate deeply into the data structure. I will use deep toString method, and this adjacency list will be converted into a string like representation that I can print. Now let us come to our main, which is here, and I have created a graph, right? I'm trying to add edges in it, and I'm trying to print it. So this I have already written before. So I'm just going to run this, and you can see the graph class we have just constructed now, right? Let us try to visualize this graph. So 1 is connected with 2, fine. Undirected graph. 0 is connected with 3. Okay, 1 is connected with 3 and 2 is connected with 3. So this is how the graph looks like. And now if you talk about the adjacency list, so 0 is connected with 3. Okay, 1 is connected with 2 and 3. 1 is connected with 2 and 3. That's correct. So list of 1, it is storing the neighbors of 1. List of 2, so 2 is connected with 1 and 3. Absolutely correct. What about 3? 3 is connected with 0, 1 and 2. So 3, adjacency list of 3 is storing neighbors of 3. This is how this 2D array. Okay, it's not a 2D array. It's a array of linked lists, right? Each linked list is denoting the neighbors of the ith node, right? That is the adjacency list implementation. I hope you are able to understand this implementation. So pretty easy, nothing fancy, nothing difficult. And if you have more complex data, as I told you, instead of having this, you can also have a hash map where key is your this will become your key, and this will be added into the list corresponding to that key, right? That's all for this implementation. Okay, so we have discussed the most commonly used implementations of the graph: adjacency list, adjacency matrix, edge list. There is one more representation that is sometimes convenient for certain type of problems. Okay, so sometimes we are given a graph in which we are saying, okay, there is a 2D matrix, and it is given that each cell is connected with, let's say, the 4 neighbors, something like this, or each connect cell is connected in the 4 neighbors which are of the similar color, right? And you have to do something, right? So in this case, what you have to do, you do not need to construct a graph. You can directly deal with the matrix, right? So if I say, okay, what are the neighbors of this one? Either it will be 4-way connectivity, it will be mentioned in the question, then you can go in these directions, or it can be 8-way connectivity. That means the diagonal directions are also included. This kind of representation is helpful in some algorithms like flood fill, right? So what is happening in flood fill? There is a 2D image which is made up of some pixel values, right? So you are filling the color until you hit the black boundary. And how are you finding the neighbors? You are going in this 4-way connectivity or doing the 8-way connectivity, right? This is not possible for every type of graph, but certain problems where graph could represent an image, right? Or the neighbors have this kind of relationship where they can be represented using a 2D array, right? So we will deal with these kind of problems in the series, and I hope you learned a lot of concepts from today's video. Again, make sure you like the video and subscribe to our channel before leaving. Thanks a lot. I will see you in the next video.